Black holes. Just saying the word sends a shiver down your spine, eh? These are some of the universe's biggest mysteries. They are like cosmic vacuum cleaners, but way more powerful. Imagine a place where gravity is king. Nothing, absolutely nothing can escape its mighty grip. Not even light, the fastest thing we know. It gets sucked in, never to be seen again. That's a black hole for you, a true enigma. Think of them as the ultimate cosmic traps. They lurk out there in the vast darkness of space. Silent, invisible mostly, waiting. Their existence stretches our brains. It makes us question what we think we know. About space, about time, about reality itself. They are nature's way of saying, "You ain't seen nothing yet. Strap yourselves in, space fans." So what is a black hole, really? Let's break it down nice and simple. Imagine a star, a really massive star, much bigger than our own sun, a true giant. This star shines brightly for millions of years. It burns through its fuel like a cosmic bonfire. But eventually that fuel starts to run out. The star's furnace begins to cool down. The outward push weakens. Big trouble brewing. Now gravity takes over. It always wins in the end with these big fellas. Gravity is that force pulling everything together. For this massive star, its own gravity is immense. It starts to crush the star. Squeezing it, the star collapses in on itself. Catastrophically. This collapse is incredibly violent and quick. All that star stuff gets squashed into an unbelievably tiny space. Think about it. An entire star, or even more mass, crushed down to a point smaller than an atom. This super dense object is a black hole. Now for the really trippy part, black holes and time. You see, gravity doesn't just pull on things like planets or light, it also pulls on the fabric of space and time itself. Yep, you heard that right. Time can be stretched and squeezed. It's not constant everywhere in the universe. This was one of Einstein's big ideas, and black holes are the ultimate proof. Their gravity is extreme, so time gets weird. Near a black hole where gravity is super strong, time actually slows down. It ticks by more slowly. Compared to time further away, that is. Imagine you have a mate brave enough, or perhaps foolish enough, to hover in a spaceship near a black hole, and you're watching them from a safe distance. Your clock would tick normally, but theirs? Their clock would seem to run slow to you. If your mate spent, say, an hour near the black hole. When they returned, much more time might have passed for you. They would have aged less than you. Section 4. Everyday time warps. Making sense of space-time. It's hard to get your head around time bending, I know. So let's use an analogy. Something a bit more down to earth. Imagine space-time. That's space and time woven together. Think of it like a giant stretchy trampoline. A flat, taut sheet stretching out in all directions. This trampoline represents our universe. Normally things move across it in straight lines, or what appear to be straight lines anyway. Now place a heavy bowling ball in the middle of that trampoline. What happens? The fabric sags, right? It creates a dip. The heavier the ball, the deeper the dip. That bowling ball is like a massive object, such as a star, or even better, a black hole. A black hole creates an incredibly deep well in space-time. A much deeper well than our sun would make, because it's so incredibly dense and compact. Now, imagine rolling some marbles near that bowling ball. If they get close to the dip, they don't roll straight anymore. Section 5, Einstein's universe, theories and cosmic proofs. This whole idea of space-time bending isn't just a wild guess. It comes from one of the greatest minds in history, a brilliant bloke named Albert Einstein. You've heard of him. Back in the early 20th century, he cooked up some amazing ideas. His masterpiece was the theory of general relativity, published way back in 1915, still holds up. This theory completely changed how we see gravity. It said gravity isn't a force pulling things. Instead, Einstein said gravity is what happens when space-time gets warped. Warped by mass and energy, like our trampoline example. Mass tells space-time how to curve, and space-time tells mass how to move. It's a two-way street. His equations predicted all sorts of strange things. Things like black holes, though they weren't called that then, and this very idea of gravitational time dilation, that clocks would run slower in stronger gravity. For a long time these were just theories, mind-blowing, but theories. Section 6. Beyond the event horizon, what we're still learning. Let's talk about the edge of a black hole. It's called the event horizon. A very important boundary. Think of it as the point of no return. Once something crosses the event horizon, it's game over. It can't escape the black hole's pull. Not even light. It's like going over a waterfall in a canoe without a paddle. There's no way back upstream. The event horizon isn't a physical surface you'd hit. It's more like an imaginary line in space. A line defined by the black hole's intense gravity. Past that line, and you're heading for the singularity, that infinitely dense point at the very center. What actually happens at the singularity? Well, that's one of the biggest mysteries in physics, mate. Our current theories, like general relativity, break down there. They give us infinities, which means we're missing something. Scientists are working hard to figure it out. They're trying to combine gravity with quantum mechanics. That's the physics of the very small. A theory of everything or quantum gravity is the holy grail. It might tell us what truly happens inside a black hole. Section 7. Why bother with black holes? Unlocking universal secrets. So, why do we spend so much time and effort studying these dark beasts? They're usually incredibly far away. They just suck things in. What's the big deal? Why should anyone care? Well, black holes are more than just cosmic oddities. They are fundamental to understanding the universe. They are the universe in its most extreme state, where gravity rules supreme and space-time gets truly bent. Studying them tests the very limits of our knowledge. They help us test Einstein's theories to breaking point. General relativity works incredibly well in most places, but near a black hole or inside one, we need something more. Black holes force us to seek a deeper understanding of gravity, and that in turn helps us understand the cosmos itself, how it was born, how it evolved, how it might end. These are some of the biggest questions humanity can ask, and black holes hold some of the clues. Black holes also play a huge role in how galaxies form and change. Most big galaxies, including our own Milky Way, seem to have one. A supermassive black hole at their center, millions or billions of times our sun's mass. These giants can affect star formation in their host galaxy. They can spew out enormous jets of energy,